Alright, so let's do a larger example with a 3 by 3 matrix. So let's consider a 3 by 3 matrix. 3, 0, 0, negative 4, 6, 2, 16, 15, negative 15, negative 5. The first step is the same. We want to solve the determinant of a minus lambda I equal to 0. I forgot to mention in the previous videos, this equation is called the characteristic equation. Notice that characteristic equation is used in chapter 5 as well for differential equations. Alright, so a minus lambda I is equal to 3 minus lambda, 0, 0, negative 4, 6 minus lambda, 2, 16, negative 15, minus 5 minus lambda, equal to 0. The first row looks really nice, 2 zeros and just one term non-zero. This is plus, so this is equal to 3 minus lambda times the determinant of the bottom right equal to 0. So let's give you 3 minus lambda times 6 minus lambda times negative 5 minus lambda minus 2 times negative 15 equal to 0. So 3 minus lambda times negative 30 plus 5 lambda minus 6 lambda plus lambda squared plus 30 equal to 0. Negative 30 and 30 cancelled, so 3 minus lambda, we have lambda squared, should be blue, lambda squared minus lambda equal to 0. So that factors into lambda times lambda minus 1 equal to 0. So there are 3 eigenvalues, distinct eigenvalues. 3 and 0 and 1 are the 3 eigenvalues. So that's step 1. Now, for each eigenvalue, we need to find an associated eigenvector. So let's move down. So let's start from 3. So for lambda equal to 3, a minus lambda I is 3 minus 3, 0, 0, negative 4, 6 minus 3, 2, 16, negative 15, minus 5 minus 3. So it's 0, 0, 0, negative 4, 3, 2, 16, negative 15, negative 8. Alright, so we want to solve the system of linear equations like this. We know the first row doesn't give you anything. To kill the 16, we do 4r2 plus r3. So we get negative 4, 3, 2, 0, negative 3, and 0. Alright, the third row tells you y equal to 0. So this goes away. And the second row tells you negative 4x plus 2z equal to 0, which tells you z is 2x. So an associated eigenvector is, so y equal to 0 and z equal to 2x. So x equal to 1, z equal to 2 is the easiest. So this is an associated eigenvector for lambda equal to 3. And now we do the same thing for the other 2 lambdas. So for lambda equal to 0, good thing a minus lambda I is just a. So it's the original matrix. So it's 3, 0, 0, negative 4, 6, 2, 16, negative 15, negative 5. So we want to solve this system of linear equations. Okay, so let's first kill the negative 4 and 16. So let's do for third r1 plus r2 and negative 16 over 3 r1 plus r3. The goal is to remove the negative 4 and 16. And then we divide the second row by 2 and divide the third row by 5, negative 5. So we get this. Okay. The first row tells you that x has to be 0. The second row and the third row are the same, so the third row doesn't tell you anything, and the second row tells you that 3y plus z equals 0, so z is negative 3y. So an associated eigenvector is, so x has to be 0, z is negative 3y, so the easiest is y is 1, and z is negative 3. We're almost there. There's a third eigenvalue. So for lambda equal to 1, a minus lambda I is 3 minus 1, 6 minus 1, and negative 5 minus 1. So it's 2, 0, 0, negative 4, 5, 2, 16, negative 15, negative 6. Alright, so let's solve systems of linear equation again. Let's kill the negative 4 and 16 again. So 2r1 plus r2, negative 8r1 plus r3, 0, 5, 2, 0, negative 15, negative 6. And let's divide r3 by negative 3. 5, 2, 0, 5, 2 again. So same thing, the first row tells you that x is equal to 0. The second and third row are the same, so the third row gives you nothing. And the second row tells you that 5y plus 2z equal to 0. So an associated eigenvector is, so we know x has to be 0, and 5y plus 2z is equal to 0. So the quickest choice is y equal to 2 and z equal to negative 5. Alright, so we are done. So let's finish with the chart. So we have eigenvalues and their associated eigenvectors. So we have 3 eigenvalues. Let's start from the last one because we can still see it. Lambda equal to 1 corresponds to v equals to 0 to negative 5. Let me peek. So for lambda equal to 0, v is 0, 1, negative 3. And for lambda equal to 3, let me go peek again, it's 1, 0, 2. So we have 3 distinct eigenvalues corresponding to 3 distinct associated eigenvectors.